All right, folks, I am continuing this video on section 14.3. And we were just talking about these trig ratios in the context of a right triangle, not necessarily the unit circle. So I can draw some picture like so. But let's be really creative. Let's draw it like this. Where here is our right angle. And let's suppose we're paying attention to this angle. So we always do this from the perspective of a certain angle. There is theta in the lower right corner. So from the perspective of that angle, we label the three sides as hypotenuse. Hypotenuse is the longest side across from the right angle. This is the adjacent leg. It's the leg right next to the angle theta. And this is the opposite leg. And we can take as a different version of our definitions, right? We have a unit circle definition for sine and cosine. In a right triangle, we can say these also, to some extent, are definitions. Sine of theta is the length of this opposite leg compared to the hypotenuse. Cosine of theta is the length of the adjacent leg compared to the hypotenuse. And tangent of theta, there's a little typo here, this should say tangent of theta equals opposite over adjacent. And as I mentioned before, people often just look at these S for sine, oops, I don't want that. S for sine, O for opposite, H for hypotenuse, SOH is a way of remembering sine is opposite over hypotenuse. C for cosine, A for adjacent, H for hypotenuse, CAH. And then T for tangent, O for opposite, A for adjacent, TOA. And we have this nonsense word, SOHCAHTOA. And if you write out SOHCAHTOA, it will remind you of these relationships. So don't be afraid of doing that. I'd rather you write out the word than misremember. And these relationships are very powerful. Why? Well, if we know an acute angle and one side of a right triangle, we can figure out the other two sides by using these. And if we know any two sides of a right triangle, we can find measures of the angles. These assume that we're using our calculator. And if you're using the calculator, pay attention to the mode. And all the time, pay attention to the relevant sides and the locations of everything, right? Everything here is about relative position. I don't want you to be thinking about, oh, I look at the top side or the short side or something like that. Really get in the habit of identifying them as opposite leg, adjacent leg, use words like that. So let's do a couple of examples. So a wheelchair ramp will start at ground level and end at a height of 4 feet. The horizontal distance covered by the ramp will be 50 feet. What is the angle of elevation of the ramp? In other words, compared to the pure horizontal of the ground, how far is it tilted up? If this were a quiz problem, I'd probably give you a picture. So here's the ground. And let's suppose we want a rise of 4 feet. That's a right angle because vertical compared to the ground would be at 90 degrees. Our ramp's going to look something like so. And we want this distance here to be 50 feet. And I want to know the angle of elevation. So that would be this angle here that measures how far up is this tilted. Compared to the pure horizontal of the ground, how much did we tilt this upwards? So here's how you want to approach a problem like this. Here's our angle. We want to look at the things we have that are relevant to the problem. Let me just rewrite this one. It looks like the word so rather than the number 50. I think I can do a little bit better. The angle is relevant because we're asking for it. 4 is relevant, that's in the problem. 50 is relevant, that's in the problem. This hypotenuse isn't in the problem, so we probably don't want to talk about it unless we're forced to. This angle over here isn't really talked about in the problem, so we probably don't want to talk about that. You really want to focus on the most important elements. Usually there are 3 of them. Usually you can focus on 2 sides and an angle. From the point of view of this angle here, the 4 is the opposite leg, and the 50 is the adjacent leg. So we want to think, all right, which is the trig function that explains how opposite and adjacent are related? Maybe you don't have this memorized, but here it is in tangent. Tangent of theta is opposite over adjacent. So let's write that down. Tangent of theta is opposite over adjacent, which in this case would be 40 over 50. I'm assuming you have your calculator. That's 0.08. And we want to know what theta is. Well, if I know what tangent is and I want to know the angle, that's where inverse trig comes into play. So theta is inverse tangent of 0.08. And let's get an estimate here. I want to do this in degrees. I will say most word problems will do in degrees because it's easier to think about and visualize. So I will do inverse tangent of 0.08 on my calculator, and that comes out to 4.574 degrees. My picture isn't quite accurate. It's more of a schematic, but it's not a very big angle. Frankly, if you're running up a hill that's 5% tilted up, you will notice that. That feels steep, even though it doesn't look particularly steep. Let's try another one. So a pyramidal structure has left-right symmetry and is 120 feet across at the base. So again, I'll draw a picture here so you understand what this looks like. So here's our side view. It's 120 feet across. And the two sides are tilted at an angle of 39 degrees. So I have left-right symmetry. This is a 39-degree angle here. This is a 39-degree angle here. And I want to know what is the height of the top of this structure. So there's the top, and I want to know how tall is that. So straight up from the bottom, how tall is that? I'll call this, I'm not going to call it h because that might confuse us with hypotenuse. Let's just call it x. We want to solve for that height. And these are right angles. Anytime we compare a vertical to the ground, you can assume that's a right angle. So for this one, there's a little bit of a trick. The entire shape of this structure is not a right triangle. But when I draw in this thing in the middle to measure the height, I notice I have two right triangles on either side and they're symmetric. So what I can do is I can take this 120 and instead say, oh, well, that's 60 feet here and 60 feet here. And I can just pick one of these triangles. So now I can just focus on this triangle on the right, and that's enough. So what's relevant? The x is relevant because I'm trying to figure that out. The 39 degrees is relevant because I asked for that. And the 60 is relevant. So from this angle, this is opposite, this is adjacent. So it's just kind of dumb luck that both of these are tangent problems. In doing more practice, you will see some that are tangent, some that are sine, some that are cosine. When I picked these pretty quickly and did not notice that they're both tangent, in class we'll do a little more variety. So we can say tangent of 39 degrees, right? We know specifically what that angle is opposite over adjacent, x over 60. I could multiply each side by 60, and I would have 60 times tangent of 39 equals x. And this can just go straight in my calculator. I need to make sure I am in degree mode. So double check your mode, change it if you need to. But I can just type this all in. 60 tangent of 39 degrees. The calculator will do it all at once. And it will tell me that this is about 48.587, and the units here are feet. So in the video, these are two examples. You will be doing lots and lots of practice, both in class and for homework. They won't all be tangent, and they won't all be word problems. But here you're getting a sense of how we can apply these ideas to either figure out a length or figure out an angle. All right, that's the end of this video.